What has this to do with combinatorics? That's the question. So the point is the following. If I have a graph, yeah, then I would like to find the two connected components. And what are the connected components? For example, this edge or this 4-click or this 5-click or this 3-click. So the main point of this talk is, if we start with a metric space, yeah, we want to analyze the idea of decomposing a graph into its two connected components. In somehow, for a metric space, we want to decompose a metric space in smaller metric spaces, so that this kind of situation happens. But I will explain that more precisely later. This has quite a few applications, for example, to computational biology and computer science. You will see my examples of computational biology. So I think everybody in this audience knows what is a metric space. So, what we want to do is we want to decompose. What did I do? Okay. We want to decompose my metric D in some things that are smaller metrics. So I will give more examples later, so don't worry if you don't understand it on this moment. So what we want is, we want to decompose and complicate a metric in some metrics which are not so complicated. So what we usually assume is that our capital D is a proper metric. That means that two vertices of 2 points cannot have distance 0 if they are not the same. But in D, you may have the situation that two points have distance 0 even if they are not the same point. Okay. So what we want? We want, this is, you see, this is a tree of all the different species. You see. So what we want is, we want to decompose. What we want is, we want to decompose the metric on the species. Where is it? Okay. So what we want is to decompose the metric into smaller metrics. So in this case, we want this, I don't think it's really working. I'm sorry, nothing is working today, but who cares? So we want to have this metric on these 2 points. That is what we really want. So I have to put that. So what we want is, we take this partition in 2 parts, B and A, and we see that there is this edge connecting the upper one with the lower one. And now what we want is, we want to make the metric, the split metric, A for A and B, so that everything in the set B has distance 0 with each other, everything in the set A has distance 0 with each other, and everything in A has distance 1 to everything in B. So that is what we want. And then if you have a tree metric, then you can show that the metric on the tree is the metric where you take the branches like this one. So for every branch we get a bipartition, and then we do the same thing for every bipartition. Yeah? And in this example I assume that my tree have all the edges have weight 1. If you want to have more complicated situation where the edges have some weights, then you have to do the constant where the constant is the constant what is on the edge. Yeah. So okay, but what you want in computational biology or phylogenetic combinatorics is to find a tree from a metric. But sometimes you find things which are not really tree. Here you have this kind of blob. That is what we call the blob. So that's where the blob of the title comes from. And here you have another blob. We want to recognize those blobs. So how can we do this? So that's one blob. There's another blob, I guess. We want to do that kind of thing. So let's go upstairs. So we want to recognize those blobs. So how do we do this? How do we find those blobs? That is the question. Okay. So that comes on to our definition of a blob decomposition. So here's, for example, here the blob. Yeah. And then you can look at what are the edges going out of the blob. And then you can say, yeah, we remove all the edges that go out of the blobs, and then you get a bipartition of the rest of the set. Okay. So, for example, in this case, you say, yeah, the distance between A and B is 2 because the distance between these two vertices where the edges are connected is 2. That kind of things. And then you do the same thing of all the blobs, and you do also over all the edges here. You do this blob and you do this edge. It's also that kind of thing. That is what we also mean by a blob. An edge is also a blob in this definition. Okay, so this is a bipartition you get from the blob. Huh? And now we look at the other bipartition of the other blob. For example, this bipartition of this blob. Yeah, then you get this partition of this blob. Then if you remove those edges, you get all the different parts of the underlying set of taxa. And you see what is important for our case is that there's a red part and a blue part where the union is a whole set. So that is very important. That is what we want to capture. That is called what is called compatible partitions. So that is what we really want. So this is a formal definition. So that's only, so that means that we have one part in one set, in one of the, we have two partitions, pi 1 and pi 2. We take a part in the existent part in pi 1 and a part in pi 2, so that the union is exactly everything. And usually you don't have to have that. But now what we want to look at is the compatible decomposition of our metric. So we started with a metric space, and now we want to have a compatible decomposition. So now for the small d, you can assign a partition of the set by saying, yeah, I can define an equivalence relation on the taxa set of taxa, by saying, yeah, two taxa are related if they have distance 0. And then you get easily, you can see that you get easily an equitable, no, what is it? Equitable partition? Oh no. Equivalence relation, I'm sorry. And the equivalence relation, if you look at the equivalence classes, that gives you a partition of the whole set, and we want that. So for each small d, you get a partition of the set, and now we want that if I take two different d's in this decomposition, that those two partitions from these two different d's are compatible with each other. So, and the second condition is that it is somehow to make it somehow non-dissonant. I mean, this is just a non-dissonant kind of condition to make, because you can take the same metric twice. Yeah, and I mean, if you take the same metric twice, then there's not really more information, and that is what exactly the second condition rules out, that you cannot take that way. Okay, so what we showed is with Andreas Ress, Cathy Huber, and Vincent Moulton is that there exists always this compatible decomposition of a metric, and there's one finest compatible partition. That is what it says. The existence is not so difficult. That's you can do fairly easy. You say, is that not? You can define something like, if you cannot decompose further, then we have that decomposition. If you can decompose, I mean, so if you have a decomposition, compatible decomposition, then you can ask for every metric whether you can decompose it further in smaller metrics, such that it works. And if you cannot do that, you get this at least one such compatible decomposition. And now the hardest part was, then you have to show that this one is unique. So the uniqueness is a difficult part of this theorem, not existence in itself. So for the uniqueness part, you need quite a bit more theory to have that. So, okay. So until how late do I have?
5 minutes.
45? It is 3:45 or 3:40? So 4 more minutes. Okay. So we'll go over this. So there is something called a tight span, and for 2 dimensions you get this thing. So this is the metric. The tight span of the metric on 2 points is a very interesting metric, no? Of 2 points, so how many metrics do you have? Essentially only one metric, and if you look at the tight span of that metric, you get this thing. Essentially the metric itself, with you combine with a line segment between the 2 points. That's what this says. For 3 it's a little bit more difficult. For 4 you get essentially one tight span. For any metric on 4 points you get essentially one tight span, and it looks like this. Of course what you could have is, you could have situations like, this can be degenerate, you can have this kind of thing. That's also, there can be also a tight span of 4 points, but that is just if you have this small, this phase of dimension 2, that you can shrink to phase of dimension 1 or dimension 0, and that is what happens here. Shrink to dimension 0. You could also have this kind of thing that you have. So this kind of things. So that is what. But the generic case is this. On 4 points you have only one metric space, often only one tight span on 4 points. And on 5 points you have 3. So now my question, on 6 points, how many do you have? 1 on 2, 1 on 3, 1 on 4, 3 on 5. Any guess on 6? Nobody. 5? 7? No. 339. So it goes very fast, and that was done by Sturmfels and you in 2007. So this was done. And then I don't know that we can do on 7 points. I mean, the factor is already 100 between 6 and 7, or 5 and 6. Then if you have another factor, maybe 10,000 between 6 and 7, then you have maybe over 3 million or so different ones. I don't think that's so easy to calculate with a computer. Okay, but that is. And then you have some programs where you can draw the tight span from metric space, that kind of things. Okay, this is what we needed. But the main point of this talk is that you need to use the tight span to find this compatible decomposition. That is the main point of this talk, so I will go over this. So here you can look at, in principle, if the so what you do is, if you have the tight span with this as the black points as my the set X, then you can draw the tight span, say like this one. And now what you have to discover, what you have to find is those blue points. That are the most important points, the blue points you have to find. And that is what you can do easily with this. So you have to find the cut vertices of the tight span. That is what you have to do. That is what you really do with the compatible decomposition. You try to find those points in the tight span. And that is the main part of the proof. To show that how to get them, how to calculate those guys. That is the main part. I think as I go too much over time otherwise, probably I will stop here. There are some applications to optimal realizations of metric spaces, which has application in computer science and so on. But I will not go into that detail today. I think I will stop here. Thank you for your attention.
Any questions?
Yes?